This is a conjugate addition reaction like we've seen in the previous chapter using stabilized enolates, and I think historically this probably came before the other reactions. So if we have a stabilized enolate, and we've seen a number of these before, these are beta keto esters, beta keto amides, beta keto ketones, beta keto aldehydes, that whole group of beta keto carbonyls that give stabilized enolates. So what we're working on here is a general reaction. If those can react with an alpha beta unsaturated carbonyl, X. X can be a lot of things here. Now, it's not just a halogen here, I'm just meaning X as the general variable. It can be H, in which case it's an aldehyde. It can be R, in which case it's a ketone. Or aryl, in which case it's still a ketone. It can be OR prime, that would make it an ester. It can be an amide, NH2, for instance. So acrylamide is a good Michael acceptor. And then there are a couple more good Michael acceptors, the electrophiles in this case, that I want you to be aware of. For instance, substituted nitriles. Now you know that a nitrile is like an ester. And then there's one other that's very useful, the NO2 reaction, and I've tried to draw the NO2 there to help you see how it relates to this carbonyl. So this is a very strong electron withdrawing group, and when we look at the mechanism in a minute, we'll see why, since this is the electrophile in the reaction and this is the nucleophile. Okay. So those are the general features and requirements of the starting material, and then this reaction occurs such that here's a specific example, and let me number the atoms for you, although I've tried to draw it in a way that I hope you can find it. If we're looking at the electrophile 1, 2, 3, 1, 2, 3, right there, here is the new bond that we made. And of course here is 4, 5, 6, and 7. 4, 5, 6, and 7. Now of course when I have the ester here, we can do things like decarboxylate, hydrolyze it and then decarboxylate it, and this makes this a very powerful synthetic methodology. So let's take a specific example here. Acetoacetic ester plus, we'll use the nitro compound, treat that with ethoxide, and I'm going to draw the product slightly differently this time. I'm going to orient you relative to the dicarbonyl compound. We do the addition. There's the new bond that we made. And then 1, 2, NO2. So here's nitrogen's 1, carbon's 2, carbon's 3, nitrogen's 1, 2, 3. Here is the bond that we made, and then 4, 5, 6, 7, and 8. 4, 5, 6, 7, and 8. All right, so those are the basic features of this reaction. Again, practice, practice, practice those specific problems. Now the mechanism. The mechanism here we need to know. We find it in other places. Soon here we're going to get to the Robinson annulation in chapter 23. And if you only learn one mechanism, learn the Robinson annulation, because it's got aldol in it, it's got elimination in it, it's got a Michael addition in it. And so everything in this chapter is wrapped up and builds to the Robinson annulation, named after Robert Robinson, the Nobel Prize winner for his discovery and its application. So the Michael addition mechanism, how does it work? Well, let's start with, say, diethylmalonate. We'll react that with the aldehyde. Now notice this aldehyde, there is an alpha hydrogen, but that hydrogen is not acidic, right? You recognize that, of course. This is an sp2 carbon that hydrogen is attached to, so that hydrogen is not acidic. The only acidic hydrogens are here. Okay, so under Michael conditions, we would then obtain as a product So again, looking at this 1, 2, 3, 1, 2, 3, there's the new bond that we made. Okay, now let's push some arrows. Ethoxide is base. Again, in an equilibrium reaction, we create the stabilized enolate. Now, this equilibrium will lie in which direction? Right, this one lies strongly in the direction of deprotonation, essentially quantitatively. The enolate is our nucleophile, so then we need to find the electrophile. The electrophile, in this case, is the aldehyde. Now, we've already seen how in conjugate addition, this is an ambivalent electrophile having a partial positive charge at both the carbonyl carbon and the beta carbon, and so the negative charge pushing the arrow from the high electron density, starting at our negatively charged atom. The pi bond swings out to make a new carbon-carbon bond. That pi bond will swing up, and we'll make an enolate. Now, how many arrows did I push? 1, 2, 3, 4. This is one of the exceptions that proves the rule for us about our rule of thumb about don't push more than 3 arrows. It's because of the conjugation here that we draw that 4th arrow. Now, I do want you to draw these as enolates, not as a carbanion, because there's really a double bond character there, and we know that from studying things where there is configurational stability. So we make a carbon-carbon bond, but as you might expect, many of these, as in many of these can be reversible. Follow my arrows, I make the enolate here. Now, the product is not the enolate, but the aldehyde, and of course we know there's an equilibrium between aldehydes and this is a non-stabilized enolate. So the pKa of an aldehyde is about what? It's around 19. Ethanol is about 16. So by a factor of about 1,000 to 1, that one will protonate and the equilibrium will lie toward Okay, so we can produce the Michael adduct. We make very significantly a carbon-carbon bond here in a controlled manner. All right, so that's the fundamentals and the mechanism of the Michael addition reaction.